Welcome to the new quantum era. I'm your host, Sebastian Hassinger, bringing you another conversation from the cutting edge of quantum science and technology. On this episode, I'll be talking with Dr. Mohammad Mirhosseini, an assistant professor of electrical engineering and applied physics at Caltech. Mohammad leads a research group developing really innovative hybrid quantum devices. These are systems that bridge the worlds of sound and superconducting circuits all at the quantum level. We'll be talking about his team's recent breakthrough, building a mechanical quantum memory for microwave photons. If that sounds wild, you're not alone. The idea that sound waves, or more specifically, mechanical vibrations at the nanoscale, could store quantum information carried by superconducting qubits really fascinated me and drew me to inviting Mohammad to come on the show. There's some really incredible implications to quantum hardware design from this work. But we'll start by unpacking what quantum memory really means in this setting and why microwave photons are essential to superconducting quantum computers and how mechanical systems like tiny high-frequency tuning forks can serve as robust, long-lived quantum storage. We'll also get into what makes this approach so promising for extending coherence times and potentially enabling scalable quantum networks through quantum transduction. It's a fascinating conversation that will change how you think about the intersection of quantum computing, physics, and engineering. I hope you enjoy it as much as I did. Let's get started. Hi, Mohammad. Thank you so much for joining me.
Hi, Sebastian. Thank you for having me.
I'm really happy that you got on. You accepted my invitation to the podcast, Mohammad, because I'm really interested in some work that you've been doing recently. I think there was a paper out at the end of last year that caught my eye. But can you start off just by sort of quickly introducing yourself and talking a little bit about how you got into the field of quantum computing?
Yeah, of course. My name is Mohammad Mirhosseini. I am an assistant professor of electrical engineering and applied physics at Caltech. I run a lab of researchers of about 10 people, and I'm glad that our recent work has been of interest to you. I got into this field basically by getting very interested in electromagnetism, the theory of electrical charges and waves in the more conventional form of it. When I was a high school student, it was very fascinating to me that very understandable range of phenomena can be abstracted into Maxwell's equations. The mathematical simplicity and the conciseness of that was very appealing to me, and I tried to pursue understanding more and learning more about ENM in my undergraduate studies. There, of course, are many technological areas or different types of systems that works based on electromagnetic fields. I found the fact that most of them are more or less understandable, frankly, a little bit boring. But then I heard about this field of quantum optics, which seemed to offer a little bit of
understood, really.
Maybe, a little bit of more confusion, and
yes.
And that plus the determinism that usually comes with Maxwell's equation explain everything intrigued me, and that's how far I remember in terms of how I got into this.
That's great. And so you ended up, I think you did your PhD at Caltech, is that right?
Not really. I did my PhD
postdoc
at the Institute of Optics at the University of Rochester in upstate New York, and joined Caltech as a postdoc previously before I started my own lab as a PhD.
Right. You were in Oscar Painter's group, is that right?
During my postdoc, I was a member of Oscar Painter's group. Yeah. That's right.
And of course, I'm in AWS Quantum, and Oscar leads the Center for Quantum Computing R&D team. So I'm definitely familiar with Oscar's work, and a huge number of really talented people have come through his group too.
And I think talking about this particular topic of our recent work, we would have to refer to a few places where his past work has been instrumental in this. So
that's great. So okay, cool. And so, getting to this work, what caught my eye was, the paper is called A Mechanical Quantum Memory for Microwave Photons. And there's a couple things that I thought somebody from outside of the field would find really interesting, just right in the title. Because for one thing, I think that, on a fundamental level, it's often surprising to people that we talk about photons in a microwave kind of setting, where as you said, the electromagnetic spectrum, we think about it, I think lay people think about it more in terms of electrical currents, maybe TV, radio, right? But the spectrum goes all the way up all the way down into the visible spectrum, right? I mean, there's sort of this continuous kind of path from microwave to photon to optical photons. And so in the microwave regime, are there actually photons within the qubit setting that you are interacting with that you're able to access?
Yeah, I mean, you're right to ask that question. Microwave photons are completely non-trivial and still fascinating concepts. Well, as you said, in electrical systems, we usually tend to think about electrons or some charge carriers that are perhaps flowing in wires, and we conventionally understand an electrical system based on them. But when we think about what happens is that these electrical charge carriers or electrons, they also interact with each other via the electrical forces. And if you think about the description of this entire system, you can keep track of these material particles, the charge carriers, or you can keep track of the electromagnetic fields that mediate the interactions among them. And it turns out that for radio frequency waves, and in particular situations where there's not particular sources around, you can essentially think of a electromagnetic circuit as a vessel where it is holding some electromagnetic energy within it. And then once you have electromagnetic energy stored in these what we call fields, then the photons are the quanta of energy of these fields when you try to describe it quantum mechanically. So that's where the microwave photon come into the picture. It is no different than an optical photon in its abstract form and its properties, but in terms of the techniques and the systems where it manifests itself, they tend to be very different. They have much lower frequency. They live inside different structures, but they are photons, for the most part. And I guess in terms of thinking about qubits, we usually do not refer to these because we think about perhaps quantum computing, where we have many qubits interacting among themselves. But what goes on is that these qubits essentially can create or absorb microwave photons. So in a rough analogy to optical systems, where we have atoms emitting or absorbing optical photons, here we have qubits emitting or absorbing single microwave photons.
Right. And so in this, again, going back to the title, mechanical quantum memory. So the next thing that I think is really fascinating is the idea of quantum memory, right? I mean, if people are paying attention to the devices that are being built today, these are rudimentary computers because they don't really have storage. They have the ability to run a single circuit. That circuit just describes a series of gates of operations on the qubits that carry out some kind of task. But there's no longer term storage. There's none of the, we sort of are very familiar with classical computing. There's both random access memory and then there's long-term storage on hard drives. There's nothing like that in the quantum computing sort of context. So is that you're attempting to add sort of longer term storage of quantum states into the sort of the toolkit of quantum computing? Is that an accurate way to describe it?
I would say so, but I would have to add some details.
Of course.
Architecturally, where do storage come into the picture when you try to do quantum computing is a non-trivial question. Depending on how you do things, you may or may not need a dedicated form of hardware just for storing quantum information. Normally, we think of qubits as entities that not only hold and create, but also manipulate the quantum information that are in these quantum states. But when it comes down to the physical properties that we need at the basic hardware for realizing these basic operations, gate operations or creation of states or storage of them, they translate to different physical properties. And what we tried to do in our work was essentially study this type of system, in this case, mechanical oscillators, where they have really exemplary properties when it comes to the storage of the quantum states, but not perhaps they're not as good when it comes to the other parts, which are, realizing gate operations, for example. So how would it come into quantum computing if you have something that can only hold the quantum state for a long time? Is that an essential component? That the answer to that question is not easy. There are cases where we think they would be needed, but our emphasis again was on the basic properties of the physical system and how it can be, utilized for these quantum operations.
Interesting. It reminded me a little bit about. I really like the work that von Neumann did at the Institute for Advanced Studies. That whole story of building that system there is very interesting. And of course, the von Neumann architecture is still intrinsically part of the classical computing context. So I believe there was a very long tube. There was a switch, a mercury switch that it would tilt, and the wave of the mercury would propagate from one end of the switch to the other, and that was their first sort of persisted state that would last beyond the length of just the individual classical circuit that was being carried out on the transistors or the vacuum tubes. So is it sort of analogous to that, where it's some mechanism for being able to hold the state longer than the qubit itself would be able to hold it?
Well, I would say that in quantum computing, the people didn't really, to my knowledge, pursue building a memory just to satisfy an architectural need. There are examples in things like quantum communication where the long propagation time of photons require for something like a memory,
right?
Essentially, right on where you begin to think about that problem. In quantum computing, it does not come up naturally in that form. All you need in the most abstract form is just the qubits. But practically, once people have tried to make better and better qubit, at least with the superconducting systems within this field, there has been these observations that it is easier to make physical hardware that can hold the quantum state in complicated form, where you can either hold it passively for a long time or you can correct for errors. But these hardware components are not perhaps best at realizing quantum gates, but on the contrary, you can make things that are really fast and they can do these gate operations, but they have a lot of dissipation. So this competition between these two different properties has essentially guided the work to areas where you have seen these primitive components, which you can call as processor and memory, right, in forms of, for example, a microwave cavity and a superconducting qubit. That's what you see more conventionally. So that has emerged. Now, architecturally, again, whether or not you need some dedicated memory to synchronize perhaps different parts of your computer that are going at different speeds, or in situations which are more similar to classical system, that is highly likely, but it goes a little bit beyond my expertise to comment on that.
So at this point, then, when the quantum memories in your paper, this is a way of extending the lifespan of the coherence and the quantum state of the qubit in the while it's carrying out its operations. Is that
that's correct? That's correct.
Okay.
Yes.
And you're doing this by getting to the third part of the title that I found fascinating. So it's a mechanical means of storing a quantum state. You're actually you're linking it through optomechanics. You're linking an oscillator, a physical device, to something that we think of as being this very abstract, quantum level device. Talk about how do you manage to physically link a mechanical device to something as ephemeral as a qubit?
Well, it is perhaps a little bit surprising to think of that, but if you think about it, well, first of all, we do have mechanical oscillators. These are vibrating dielectric components, which sometimes we think of them as tuning forks. They oscillate at frequencies that are pretty high, gigahertz frequencies, and what we do is actually we convert electrical energy or electrical quantum states, to be more specific, that are created by qubits, superconducting qubits, into mechanical vibrations or quantum states that are encoded in the vibrations inside these mechanical oscillators. It may sound a little bit surprising, but this interplay of electrical signals and mechanical vibrations is something that happens in microphones and speakers. So in some forms, it's very natural. It comes up naturally almost.
It's true. I guess what's surprising is the idea that down at the quantum level, I mean, does that mean that mechanical vibration is quantized at that scale?
Well, to our knowledge, quantum mechanics is the underlying theory for understanding basically everything around us. What makes this perhaps a little bit less usual or less familiar is that normally we do not have to invoke quantum mechanics to understand vibrations.
Right.
There's this field of acoustics, for example, right? We've conventionally made systems that we can fully understand with classical theories. What makes the quantum mechanics necessary in this experiment and other experiments of this type, I have to say we're not the first people who thought about doing this, is that once you have a what we call a non-classical state, you essentially use this qubits in these types of systems to generate states of motion which have genuinely non-classical properties. They manifest signatures that are not understandable without using quantum mechanics. It is this creation of these relatively exotic states that makes us talk about single excitations of energy, phonons, or quantum mechanical states of mechanical oscillators. But again, in this context, if there is an oscillator of any type, whether it's electric, optical, mechanical, or any other type, if you think about it in terms of its quanta of energy, there are single excitations. They might have different names like photons or phonons for electromagnetic and mechanical variance, for example. And then if you have a quantum state, it is in principle possible to map it from one degree of freedom to another by essentially converting the quantum state one photon or one excitation at a time.
And the you just mentioned phonon, so that's the sort of terminology for the quantized unit of mechanical oscillation. Is that right?
Exactly. This is a phonon to a mechanical oscillator is a photon, is what a photon is to an optical cavity. It's a single excitation of energy.
And so you mentioned tuning forks. I mean, that's a very familiar sort of, it's visceral, right? You can hit the tuning fork and then put it on something that's going to resonate like a table and you can hear the tone. Is that, I mean, at the very, very smallest scale, is that the same kind of principle that you're using to link the two-level system of the qubit to the oscillator?
Yes, very, very much so. I mean, these are the structures we make are smaller a little bit.
Yeah, a little bit smaller.
A few microns, but they're still made of many, many atoms. So in that sense, there are still components that in some sense resemble a tuning fork. The frequency they vibrate at, as I mentioned, is much, much higher than what we hear. We can perhaps hear about a few kilohertz, but these are at gigahertz frequency, and they sit in vacuum for technical reasons, so we cannot hear them echoing. But otherwise, they are the similar things.
You couldn't use it to tune a piano, but other than
perhaps,
and so of course they would have to be in the gigahertz range because that's the microwave frequency range that is used to control and read out a qubit, typically a superconducting qubit.
That's right.
Is it difficult to sort of match the microwave regime with this mechanical oscillation frequency to link the two systems?
There is a couple of different things. I mean, you mentioned I would perhaps talk about them one at a time. In terms of frequency, usually mechanical oscillators, operate at lower frequency in more standard settings like room temperature and ambient pressure. It is very difficult to operate with gigahertz frequency resonances. They tend to dissipate their energy really fast. They involve really small dimensions. So unless there is a very good reason, usually they do not show up in the technologically relevant devices. But for cryogenic experiments at very low temperatures and conditions like vacuum, which we already need for superconducting qubits,
Right.
the experiments with these gigahertz frequency oscillators are much easier. They are a little bit smaller, but otherwise they are relatively easy to work with. In terms of the mechanism for coupling them to the electrical domain, essentially how to convert these quantum states from a qubit into a mechanical oscillator, well, that is basically where most of our work has been. There are different processes that you can use to do this conversion. And, in the quantum world, we care about ultimately how well we can get interactions between two elements, while at the same time avoiding what we call decoherence or dissipation. So there's always a competition between these interaction rates that are things we want to the dissipation rates that are things we want to avoid. And the research basically in linking these mechanical oscillators to microwave qubits is in maximizing this ratio between coupling and dissipation.
Interesting. And in terms of, coherence times are one of the critical factors in quantum computing. It's one of the things that, different modalities or different designs within a particular modality are constantly seeking. When your work sort of coupling these mechanical resonators mechanical oscillators to the two-level system, what's the sort of potential gain in coherence times do you think that might provide?
Yeah, so I guess I have to give some extra context here. Well, as you said, coherence time is what you care about. Ultimately, coherence time is is the metric of how long we can preserve quantum coherence, which is essentially the resource in trying to use a quantum state for any application. There is a slightly different concept of a lifetime, which is related to a coherence time, but is not exactly the same, which is the amount of time a system can retain the energy you put in it. Now, these sound very similar, but they're a little bit different because for quantum states, you care about preserving the energy, but you also care about preserving the phase. Phase is a very significant component of what you care about. And there are systems that can preserve energy for a long time, but necessarily the phase. So the system we work with is what is very exciting about it is that they have extremely long lifetimes. They can preserve energies in terms of phonons for times that exceed what superconducting qubits can do by more than 10 times, perhaps about 30 times or so. Now, when it comes to coherence, this picture is a little bit more complicated. We see signatures of processes that can cause dephasing. So in terms of coherence time, the improvements are a little bit more modest, a factor of few with current experiments. But without going to too much detail, I would say that there are techniques where these dephasing processes can be mitigated, and ultimately, with proper control, coherence time can be extended to the limits where the lifetime is the relevant time scale. And there we would, expect that this factor of 10 to 30 would be, the improvement over qubit systems.
That's amazing. And you're talking about the difference between T1 and T2, essentially.
Exactly.
Yeah,
exactly.
Okay. So T2 is the dissipation time, essentially, right?
T2 is energy dissipation plus dephasing. T1 is just energy dephasing.
Right.
Energy dissipation,
Okay. Yeah.
So we have about 30 times larger T1, but our T2s are only a factor of few.
Oh, okay. I got it. Okay. That's great. So that must be actually, one of the sort of rivalries between like the neutral or trapped ion based systems and superconducting based systems is that the atom based systems like to say that they've got orders of magnitude more sort of lifetimes of their qubits. This is a way of potentially making superconducting more competitive with the atom based modalities, I guess.
Yeah, perhaps. And I have to mention that there is a number of studies with mechanical oscillators of very different shapes oscillating at very different frequencies and made out of very different materials where they can get to massive lifetimes, several seconds, even minutes in some systems. The challenge has been in trying to observe these exciting properties at the single phonon level, where you can precisely put a quantum state there and look at the phase, what happens to the phase, what happens to the energy, and observe that decoherence process. And that is perhaps where our work may stand out, because we have been able to do that observation on one variant of mechanical oscillator. And now that we, in some sense, see verification of these really exciting properties, there is hope that with different types of oscillators, we can potentially achieve a much, much larger benefit down the road.
And I mean, it seems like there's a trade-off in general. Both the atom-based and also things like NV centers, for example, have very, very long coherence times, but they're very, very slow, right? The claim to fame of superconducting qubits is the speed of gate operations and readout. Is there any kind of speed penalty that is associated with adding this mechanical oscillator to a qubit?
It's a very, very good question. Yeah, I mean, like you said, to get to very good coherence times, you want the most isolated system in the world. But then, how would you use it if it's really isolated, right? So the challenge is
there might be an immortal qubit somewhere, but we would never
exactly
know.
Right. Exactly. And there are systems out there, right, that have hours coherence times, but they're not so easy to operate. Yeah. So the key is to selectively access, I guess, interaction to an entity you care about, and then essentially turn that interaction off when you don't want it. And the same types of trade-offs do show up, in fact, in our work. The fact that what enabled our experiment has been the specific process that we have used to couple mechanical motion to electrical signals. And in this type of process, the optomechanical process that we are using, we are able to retain these large coherence properties of these mechanical oscillators, but the rate of quantum state conversion from electrical domain to mechanical domain remains slow.
Okay.
So it's about 100 times slower than what you can do with just a superconducting qubit. So there is a speed bottleneck right there in terms of converting the quantum states from one domain to the other. However, I mean, there is a lot of room for improvement because this is the first time we have done something like this. We think we can improve it quite a bit. How far it would go ultimately, it's a very difficult question to answer beforehand.
Yeah, of course. Sounds like a combination of sort of iteratively, like the engineering, the fabrication, the design, sort of iteratively trying to improve it. And then, of course, not knowing scientifically with the fundamental limitations of how far you can go with it. And is there any impact of in this kind of coupled system on the error rate? Is there either an increase or decrease in bit flips or phase flips?
Well, this improved lifetime or this improved in T1 can be interpreted as a reduction of the bit flips in this context, and the T2 coherence time can be the dephasing component of the T2 can be translated as phase flip. So reiterating what I said previously, I would say that we are seeing a order of magnitude reduction of bit flip errors and a very modest improvement in phase flip.
So potentially these types of qubits coupled to quantum memories, optomechanical quantum memories, might have lower overhead to get to fault tolerance, right? In terms of an error correction code.
Well, maybe, but I mean, to answer that question properly, one has to remember that the error rates only become significant or relevant when we consider them in the process of realizing a quantum gate. So we need to be able to do a quantum gate and then look at the error created during that process. It's very different than our experiment where we have had this quantum state sitting stationary in an object and looking at it just at a later time. So in terms of, we have not yet done any sophisticated type of gate operation on these oscillators.
I see.
It is in principle possible to do it. There is work with microwave frequency oscillators, essentially RF cavities that are also combined with qubits to make an architecture for long-time storage plus gate operations. But for our system to achieve that realm, we need to improve essentially these coupling gates that we talked about.
I see. So in that context, then, the gate operations would have to be performed on the optomechanical coupling itself, or the device itself, or that aspect of the device.
Yes.
Yeah,
So right now, in these more primitive types of experiment, like the one we did, we shuttle states back and forth between the qubit and the oscillator. We make something, put it there, revive it later. But with more coupling, what you can do is you can have the qubit to be always coupled to the mechanical oscillator or the oscillator or the long-lived oscillator. You would design this system such that they do not interfere with the operation of each subparty too much. So the qubit lives there, the oscillator is there, but the presence of the qubit and its interaction with the oscillator will create some sort of nonlinearity in the spectrum of the oscillator, and that allows you to essentially take benefit of the qubit presence to do gate operation in the oscillator or on the quantum states that are put into the oscillator, while at the same time preserve the long coherence time of the oscillator. So that it's a hybrid architecture where the qubits are there essentially for these gate operations, even though you don't actively use them all the time. And that's what we are hoping to move towards.
Interesting. And I guess the background of this work was, I think, explorations in transduction, right? Which is sort of the idea of taking a microwave qubit or a qubit in a microwave frequency and trying to transduce it into a telecom frequency or a flying qubit, a photonic qubit. And this has obvious, huge advantages in scalability, right? If you can, in superconducting devices are limited to some degree by how much you can fit in a dilution refrigerator. If you could span from one dilution refrigerator to another through these photonic links, photonic to microwave links, that would be really exciting. And of course, obviously, you mentioned quantum networking and quantum communications before. It seems like that transduction would be really critical there too. So is this quantum memories application of optomechanical coupling, does that have any implications for the work you've done prior in transduction?
Yes, you're absolutely right there. The mechanical oscillators surprisingly keep showing up in several areas in the close vicinity of superconducting qubits. And like you said, the optomechanical nonlinearities are one of the best ways we know to map a quantum state from the mechanical domain to the optical domain. So if you have a way of connecting electrical domain to mechanics and then a way of going from mechanics to optics, that naturally gives you a way to transduce microwave frequency quantum state to optics. In terms of practical impact, the type of mechanical oscillators that we have used in our current experiment is exactly the same type that is commonly used in optomechanical experiments. So the techniques that are developed in the course of our experiment, we think can be readily applied to also microwave to optical frequency conversion, essentially by using the same oscillator as an intermediary. And we look forward to exploring it.
Is it safe to say, sort of like, very crudely, that you're taking electromechanical, microwave frequencies and having that vibrate the optomechanical the device, and then that essentially is flipping on and off or affecting the optical regime? It's essentially just bridging those two worlds in a sense.
No, exactly. It's exactly what you said. It's not crude at all. You can think of an electrical signal shaking the membrane on a speaker, and then laser light reflecting off of it, dance on the wall. That's exactly what's happening. Yeah,
it's so mind-blowing to think about that happening at that tiny scale. It's funny because it feels like what you just described, we have direct, physical experience. So we have good intuition for that kind of, speakers, microphones, light bouncing off of surfaces that are vibrating. And yet it still seems so impossible to try to translate that intuitively into that microscopic scale that you're working at. So it's really fascinating. What do you like? That last paper was December. What's sort of the next phase of work for you and your group?
So, in terms of the applications, you already hinted a few areas where we are thinking about. We think that the coupling rate between electrical and mechanical domains can be improved quite a bit, and that would enable us to do more sophisticated operations that are relevant to quantum computing. That's one area we are pursuing. taking these mechanisms and using them for microwave optical transduction is another area, this is something we are also exploring actively. I would add a third component, which we are very excited about, which is if these mechanical oscillators also have a lot in common with qubits when it comes to their sources of decoherence. Usually we treat decoherence as some existing environmental condition or precondition that these devices have and they suffer from. But in terms of for superconducting qubits, we know that two-level system defects are essentially defects within atomic defects within material systems that are the bottleneck. It turns out that the same two-level system defects also create decoherence in mechanical oscillators. They are also the major source of decoherence in these oscillators. But despite that, the mechanical oscillators tend to achieve much better lifetimes and coherence time than the qubits. That's a little bit puzzling. It's partially understood by the community, and it's been often attributed to the size scales. These oscillators are thousands of times smaller than qubits, and that just allows them to have less atoms and less defects within those atoms. But there are effects that are also a little bit less trivial than that. So one of the things we're trying to understand is to look at the interplay between mechanical motion and these atomic defects in these systems, and we think that would be very interesting because it can potentially allow us to make better mechanical oscillators, but a better understanding of what these defects are and how they interact with other systems can also be beneficial to superconducting qubits. Ultimately.
Because you're seeing similar behaviors from similar roots in two very different settings. So the comparison between the two may actually be
exactly.
Yeah, interesting. That's fantastic. That's terrific. Well, thank you so much, Mohammad. I've really enjoyed the conversation. I appreciate your time.
Thanks for having me. I also enjoyed it, and it was great.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.